All right, so for this fifth one, we have that line L1 is tangent to a graph of a function f of x at the point 3, 1. Line L2 is given by the equation blah. Okay, so all of this is L2 and is perpendicular to L1. Okay, so there's a lot of buzzwords going on. Let's see what's happening. So for part A, we have to write down the gradient of L1. Ooh, look at that, another buzzword. See? So let's go bit by bit. Okay, gradient, all right, is the same as slope. Okay, and in your formulas, you're going to see that gradient is actually what they call m. Okay, and if you go into the formula booklet and you look for your gradient, there it is, the gradient formula, m equals blah. See? So just so you know, I'm taking this from the formula booklet, okay? From the formula booklet, we have that m equals y2 minus y1 divided by x2 minus x1, see? Now the slope of anything, okay, is basically its rate of change, see? So if you have a line that looks like this, okay, kapow, its slope is going to be, well, what's the distance from this point to this point? That is your slope, okay? Now, see what I just drew. On the one hand, you have the thing in green, which is kind of like this y2 minus y1, okay? And on the other hand, you have what I'm putting now in, let's say, yellow, okay? And in yellow, we have the part of x2 minus x1, okay? So basically what I'm trying to tell you is that for calculating your slope, okay, your m, your gradient, you are seeing the change in horizontal. You're seeing the change in vertical because your y values are your vertical divided by the change in horizontal, okay? Because your x is your horizontal values, all right? So that's just a little bit of a chit chat about what gradient is, what slope is, okay? When we have lines, there are different kinds of slopes that can appear, okay? If you have what we call parallel lines, okay, this would be a case of parallel lines. All right, this is parallel. Why is this? That is a P, not an R. This is parallel because the first slope of the first line is equal to the second slope of the second line, okay? These are lines that will never touch because they're parallel, okay? If they were just a little bit different in slope, okay, just a little bit different, eventually, eventually they would touch each other, see? Way down the line, but they would, okay? So when they're parallel, they never touch, all right? This is a case where they're almost parallel, but as long as they're not parallel, they're gonna touch eventually, okay? Whatever, fuck it. You have the case of parallel lines up here, see? The case of perpendicular lines, which is what this exercise has, is when it looks like this. Kapow, kapow. Literally, okay? You're gonna have the first line here, the second line here, okay? What is happening in this case? Well, as you can see, one of them is sort of like the inverse of the other, okay? So if for parallel, if for if for parallel we had that the first slope is equal to the second slope, for perpendicular, which is what I drew just now, you're gonna have that the first slope times the second slope equals -1, okay? And I know that it's for some people this is like good enough, and for the other people they're like, what the fuck is going on? So a better way to understand it, in my opinion, is that perpendicular slopes is you flip it. So you're first gonna flip it, and then you're gonna multiply by -1. For example, for part A, here you have this line, ¿cierto? The line of the equation, y equals blah, blah, blah. See? The line of this equation, so y equals -1/2 x minus 5 over 2, because it's a normal line, okay, it's not a parabola, nothing weird, because it's a normal line, it comes from this world. It comes from the world mx plus b. What do we know about this line? We know that b is the y-intercept, and we know that m is the slope. So, if this is the slope, of L2. See? And we know that L2 is perpendicular to L1. How do I find the slope in L1? Well, because they're perpendicular, I flip it and I multiply by -1. So I'm going to take this -1/2. I'm going to flip it. So for the first I'm going to flip. Okay, here's the flip. Da, 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 da. Flip it. And then I multiply by -1. So if I multiply by -1, it's going to look like this. I end up with 2 over 1, which is just 2. Okay? So intuitively, you can remember that you have to flip it and then multiply it by -1. If you want the math answer, you can see it here. So if m1 times m2 equals -1, that means that m1 is equal to -1 divided by m2. And so see how m2 is on the bottom now, that is the flip part. And see how there's a -1 up here, that is the multiply by -1. Okay? Anyways, fuck it. For perpendicular slopes, okay, you flip it and multiply by -1. So let's do another example. Let's say that your slope is -4. And I say, yo, this is the slope of L1. L2 is perpendicular. So if the slope of L1 is -4, the slope of L2 is going to be 1 over 4. What if I tell you it's 2 over 3? For L2, it's going to be -3 over 2. What if I have, I don't know, -69 divided by 420? Well, I'm going to flip it, times it by -1, ends up being positive. See? So really look at these 3 examples, really try to absorb it, and you should be fine. Okay, if you understand these 3, you understand perpendicular lines. See? Rule of thumb, flip it, multiply by -1. You should probably write that down somewhere. See? Anyways, whatever, that is part A. So for part A, you literally just put this m1 to show that the slope of the first one is going to be 2. Let's move on. For part B, we need to find the equation of L1 in the form y equals mx plus c. Remember how I wrote mx plus b? Sometimes they write mx plus c, okay? The idea is the same. This is still the y-intercept. This is still the slope, okay? Anyways, for part B, what I suggest is this fancy line that I'm pretty sure is in your formula booklet. Let me just double check. So here I have, oh, actually here it says, so equations of a straight line, right on top, see? There are 3 ways to write the equations of a straight line. You have the first one that I showed you, okay? You have this one in the middle, which is kind of weird. They usually ask for the answer in this form. And you have this one, this last one. Okay, this one is the most useful, okay, in my opinion. This is what they call point slope form. Now, guys, I need you to keep this in mind. It's super important, so I'm going to slow down. Point slope form is what you're going to use to start your exercise, okay? From point slope form, you can go to this very easily, and you can go from here to here very easily, okay? Technically, you can go from any of them to any of them, okay? But point slope form is particularly useful to go from this form to this one, okay? So use point slope form for what? For starting, ladies and gentlemen, see? So let's go to part B. Let me make a little bit of space because I did a lot of chit chat in the beginning, although I think it was useful chit chat, but that is for you to decide. So for part B, what do we know? So first of all, we know that, what do we know about L1? So we know that L1 has the slope from part A of 2. What else do we know about L1? Tell me. Take a second, read what we have. What else do we know? There's got to be something else. See? Ah, L1 is tangent to the graph of a function at the point 3, -1. Some of you are probably thinking, what the fuck is a tangent? So, let's say you have a parabola like this. Okay, so this is my parabola f of x. See? I can have, let me just, whatever. It looks like this, okay? And let's say that at x equals -2, okay, I'm just making this up. At x equals -2, we have a tangent. So a tangent is a line that touches my function once and never again. Okay, so usually it looks like this. It touches here and never again. See? I can have a tangent, let's say at x equals whatever, 3, okay? And it would probably look like this. It's going like this, going like this, going like this. Boom! Barely touches right there. See? That would be another tangent. Okay? So that is the idea of a tangent. Touches once, never again. Touches once, never again. So, why is it useful that L1 is tangent to the graph of a function f of x at the point of 3 comma negative 1? Well, think about it. At 3 comma negative 1, conveniently I put it right here. Okay, this is a made up example, by the way, see? But there is something important to notice here. So, at 3 comma negative 1, L1 is passing through 3 comma negative 1 and f of x as well. So, what am I trying to say? It is, ladies and gentlemen, a point that they share. So if it is a point that they share, it is a point that they both have. Ah, okay. So what you're telling me is that L1 basically has the point P, 3 comma negative 1. That is what it's telling me, okay? The tangent thing might be relevant later, but for now, this is all we know for part B, and it is also all we need for part B. And you're going to see why in a second. So let me leave this over here. It is a point that they share, see? So, as I said, point slope form is what you're usually going to use to start these exercises. Okay, so point slope form from the formula booklet, this last one looks like this. We will have that y minus y1 equals m parentheses x minus x1. So, what do I need to fill in to use this? I need to fill in y1, x1, and m. Y and x are just variables, see? It's no different than this y and this x, see? So, this x1, y1 is just a set of points. Literally, okay? If you ever face something that says x2, y2, that makes reference to my second set of points, okay? Notice how this 1 goes with this 1, this 2 goes with this 2, okay? As long as you're consistent with that, you are doing things right, okay? So, whatever. Point is, this little one and this little one here are telling me that they're the x's and the y's of the same point. And so in this context, because I have the point P 3 comma negative 1, x1 is 3, y1 is negative 1. M is 2 because I got it from part A, and I can now plug in. So I'm going to have y minus minus 1 equals 2 parentheses x minus 3. Notice, just a quick comment some of you could really use. Here, I plugged in parentheses, okay? Ladies and gentlemen, always plug in parentheses. The reason it is worth it to get used to plugging in parentheses is that way you avoid the problem of the double negative, okay? For me, it's much more apparent that there's two negatives here when I plug in with parentheses. If I were to not plug in parentheses, something we've probably all done, I might have just plugged it in like this. I literally might have just done that, okay? And so to avoid that issue, make sure you plug in parentheses. See? Just a quick comment might be useful. Fuck it. So on the left side, I end up with plus 1. On the right side, I end up with 2x, because I multiply like this, minus 6. So y equals 2x minus 1 minus 1. Careful with the negatives, negative 7. That is part B, literally. And now, last but not least, for part C, we have that show that L2 is not the line that is normal to f of x at point P. Ladies and gentlemen, there's probably 90% of you that are thinking, what the fuck? What? I mean, what? What do you mean normal? What's happening? Say, guys, I got it. So, remember how I said that you can have a line that is tangent. See, so let's say you have this parabola, you have this guy here that is tangent, okay? So the scenario where it's tangent, okay? There's a scenario where it's tangent. You have the slope of the first line, okay? The slope of the first line being equal to the second line, see? When you have a normal, I'm going to put it in red. When you have a normal, the slope of the first one is equal to the slope of the second. I'm not sure why I put an L there. When you have a normal, the slope of the first one is perpendicular to the second one. Okay, when it's a normal, the first slope is perpendicular to the second one. So a normal would actually look like this. All right. Let me just put M3 here so that we understand we're talking about L3. Okay. So just following my example, like whatever, fuck it. When it's tangent, the slopes are the same at that point. Okay. When it's normal, the slopes are perpendicular at that point. Okay. Whatever. You got it. So you can sort of associate tangent to like parallel because the slopes are the same, and the normal to perpendicular. See, maybe that helps a little. And yeah, what's the key difference between these two? Well, that the tangent is at that point the same slope, and that the normal is perpendicular slope at that point. See? All right, cool. So for part C, show that L2 is not the line that is normal to f of x at point P. So, what can we do? There's a couple of ways to really sort of approach this, okay? The first one we can do is that we can consider point P, see? And so the first thing we can do is seeing if point P, okay, is in L2. If point P is not in L2, then L2 has nothing to do with it, see? Let's see what happens. So L2 is this guy here, see? So L2, we know, is y equals negative 1/2 x minus 5 over 2, see? We know that point P is this one here, 3 comma negative 1. So let's go ahead and plug in. See, so if I plug in P, I end up with negative 1 equals negative 1/2 times 3 minus 5 over 2. In other words, negative 1 equals negative 3 over 2 minus 5 over 2. What is this telling me? It's telling me that negative 1 has to equal negative 8 over 2. What does this mean? That negative 1 equals negative 4. Guys, there ain't no trick here, okay? Does negative 1 equal negative 4? No. 1 apple does not equal 4 apples. So what you can say as an answer, literally, is that L2, and this would be your answer, L2 doesn't have the point P, so it can't be the normal line. Because it doesn't even touch. I mean, it can't even be tangent because it doesn't touch it. See? That is the main method you can try to do. Okay? There's a couple other methods, but I don't think it's worth going into them. I'm just going to leave you with this tool. Okay? If you plug in P and you get something weird like negative 1 equals negative 4, it's not part of the line. Don't worry about it. Okay? There's two other methods. You can check the answer key in a bit. But basically, stay with that. Okay? You can attempt to show that P doesn't lie on line L2. You can attempt to find the equation, but that is a little more annoying. And intersection is a little easier, but still, okay? Stick to the most intuitive one, okay? I'm not going to show you all the tools because you guys don't need, I mean, ideally you have all the tools, but guys, I'm just trying to explain this one problem, okay? For this one problem, the most direct approach is plug in P. If it doesn't work, move on, okay? L2 is not the normal line at LP because it does not lie on L2, see? This is no different than what I told you just now, okay? I just told you that L2 doesn't have the point P, so it can't be the normal line. What's happening here if you're still not convinced. What's happening here is that you have the line f of x, let's say something like this. Okay, let's say that this is f of x, okay? And let's say that I have my line, I don't know, L2 that goes like this, okay? What we're saying is that, yo, at 3 comma negative 1, which is here, L2 is the normal. And it's not, because at L2, L2 doesn't even touch f of x, okay? Even more, what's truly happening, sorry, I actually messed up here. What's truly happening is that the point 3 comma negative 1 is this one. And so 3 comma negative 1 doesn't even fit in L2, okay? If it would have fit, then you need to see the slope and see if it's the same slope as f of x, okay? In this case, it doesn't even, this point doesn't belong to L2, okay? So if it doesn't belong to L2, we don't care about it, fuck it. All right, this last explanation was a little long, but although I did do a lot of blah blah, I covered all things and I'm sure it helped. See? So anyways, I hope it helped. I'll see you around. Moving on with number 6.